Dear learners, the present lesson is a part of series of lectures on Newton's laws of motion. In this current part 2, we will be talking about the quantitative definition of force, the second law of motion, SI unit of force, the third law of motion, the principle of conservation of linear momentum, and the examples illustrating the use of conservation of linear momentum. In the previous lesson, we studied the effects of a force through our observations in day-to-day life. Through critical analysis, we discovered that the force is a push or a pull or a hit which changes or tries to change the state of rest or uniform motion of a body. Remember that physics is a branch of science in which we observe a phenomena, carry out measurements, analyze the data and correlate the quantities measured. The first law of motion led us to a qualitative definition of the term force as used in physics. The second law gives a quantitative meaning to force. It measures the extent of change which a force F brings in a body of mass m. The law relates force applied on a body to its momentum. According to the law, the rate of change of momentum of a body is equal to the force applied on the body and is in the direction of the force. We write force equal to rate of change of momentum equal to change in momentum divided by time equal to final momentum denoted by Pf minus initial momentum which is denoted by Pi divided by time. We know momentum is product of mass and velocity. So, final momentum is mass into final velocity v minus initial momentum mass into initial velocity u over t, which equals m into v minus u over t, but v minus u over t according to equation of motion is acceleration. So, we get F equal to m into a. Hence, force is the product of mass and acceleration. This is Newton's second law of motion. SI unit of force. The equation F is equal to ma helps us to define SI unit of force. The unit is called Newton. It is denoted by capital N. Here I will like to mention one thing. The name of a unit never starts with capital letter. Capital N Newton will mean Sir Isaac Newton. The unit is always start with small letter n. We have 1 Newton equal to 1 kg into 1 meter per second square. For definition of SI unit, we say 1 Newton is the force which produces an acceleration of 1 meter per second square in a body of mass 1 kilogram. To further explore this quantitative relation, consider the following experiment. Figure 1 shows an unextended elastic spring. The force applied to the spring is 0. Figure 2 shows extended spring with a mass attached to its free end. The pull develops a force kx in the spring towards left. The acceleration produced in the bodies of mass m1, m2 and m3 respectively are measured as a1, a2 and a3. Measurements show that for a given force F, we get F equal to m1 into a1 equal to m2 into a2. From the above equation, we see that for the same force applied to the two objects, we have m1 a1 equal to m2 a2 or m1 over m2 equal to a2 over a1. Hence, for a given force, smaller mass implies larger acceleration and vice versa. The equation you can see it is m1 over m2 equal to a2 over a1. Now, let us go on to Newton's third law of motion. The second law relates the external force on a body to its acceleration. But what is the origin of the external force? Which agency provides the external force? Let us explore the origin of the force. Consider a coiled elastic spring fixed at one end. Let us apply a force F on the free end of the spring. The force of the extended spring can be felt on the hand. Hence, in this case, two forces are acting simultaneously. The force of extended spring on the hand, force due to the spring on the hand, we write it as FHS. The two forces are related as FSH equal to minus of FHS, that is action equal to minus reaction. This is third law of motion. According to the law, to every action there is always an equal and opposite reaction. It should however be noted that action and reaction act on different bodies and do not cancel each other. The law holds even if the bodies are not in contact. The earth pulls a stone towards itself due to gravity. Does the stone also exert a force on the earth? The answer according to Newton's third law is yes. The stone exerts an equal and opposite upward force on earth. But we do not notice this force as earth is very massive. The effect of a small force on the motion of the earth is negligible. Following points are important when we apply third law of motion. Forces always occur in pairs. Force on body A due to B is equal and opposite to the force on body B due to A. There is no cause effect relation between these two forces. The two forces act at the same instant. Either of the forces can be called action and the other is called the reaction. Action and reaction forces act on different bodies and not on the same body. The motion of A is governed by FAB, that is force due to B on A, and the motion of B is governed by FBA, that is force on B due to A. Let us now take an illustrative example of third law of motion. Consider a bullet gun system. When a bullet is fired from a gun, the bullet moves forward and the gun recoils, that is, it moves in the backward direction. An important implication of the law is the total number of forces in nature is always even. This is because an action will immediately evoke an equal and opposite reaction. So, a single force cannot exist in nature. We always have an action and reaction pair. That is what leads us to the conclusion that the total number of forces in nature will always be an even number. Now, let us consider an extremely important principle in physics, the principle of conservation of linear momentum. This is a principle which is never violated under any circumstances, be it microscopic objects, subatomic particles or the large mass particles. The second and the third law of motion lead us to an important fundamental law in physics, which is known as this principle of conservation of linear momentum. It states that if the net external force acting on a system is 0, the total linear momentum of the system remains constant. Now, let us prove this principle for a single isolated object. For an isolated object, momentum conservation follows from law of inertia. Consider an object of mass m moving with a velocity v. If F is 0, that is, if the external force acting on a body is 0, the law of inertia implies that the velocity will not change, that is, it will remain constant. As the mass is also constant, the product mv of or the momentum of the body remains constant. This verifies the principle of conservation of linear momentum for a single object. Suppose two bodies, body 1 and body 2 collide. Let us further suppose that no other forces act except the forces of their mutual interaction. Let body 1 exert a force F21 on body 2 and body 2 a force F12 on body 1. By third law of motion, these forces must be equal and opposite. Thus, we get F12 equal to minus of F21. According to Newton's second law, F12 is equal to dP1 over dt. This follows from the relation force equal to rate of change of momentum. And for body 2, we can write F21 equal to dP2 over dt. Also, F12 plus F21 equal to 0, the forces being equal and opposite. This implies ddt of P1 plus P2, that is, the total rate of change of momentum of the two bodies is 0, or P1 plus P2, the total momentum of the two bodies is constant. Let us now see what will happen if we have a large number of objects forming a system. In general, for a system with n objects, we have total linear momentum P equal to P1 plus P2 plus P3 and so on up to Pn, that is the vector sum of all these momenta. Also, the rate of change of momentum dP over dt is equal to net external force. Now, according to the condition laid in the principle of conservation of linear momentum, if the net external force is 0, we get dP of by dt or the rate of change of momentum as 0, which implies that the total momentum P is constant. This verifies the principle of conservation of linear momentum for n body system. Let us now consider some examples which illustrate the principle of conservation of linear momentum. What happens if a stationary block explodes into several pieces? For a stationary block, the initial momentum is 0. Suppose the block explodes. To conserve momentum, the sum of the momenta of all the pieces must add up to 0. That is, P final equal to P1 plus P2 plus P3 plus P4 plus P5 is 0, where P1, P2, P3, P4, P5 etc. denote the momenta of individual pieces into which the block has exploded. Let us now take another example of the same principle. Take a bullet gun system at rest. Since the system is stationary, the total momentum of the system is 0. What will happen when a bullet is fired from the gun? The bullet moves forward with a large velocity denoted by small v, and the gun recoils with a small velocity denoted by capital V. For the system of bullet and the gun, we have P initial equal to 0. Therefore, P final, which means the sum of the final momenta of the bullet and the gun, P bullet plus P gun equal to 0, or M V bullet, which denotes the momentum of the bullet, plus capital M, the mass of the gun, into velocity of the gun. The momenta add up to 0, which gives velocity of gun as minus of small m, that is mass of bullet, divided by mass of the gun into velocity of the bullet. Hence, we get velocity of the gun far less than velocity of the bullet. This is because the momenta of the gun and the bullet are equal in magnitude and opposite in direction, but the speed of the gun is very small as compared to that of the bullet due to its larger mass. There are a very large number of examples wherein we can apply this principle of conservation of linear momentum. It is valid even when the particles are subatomic, and equally true when the bodies are very large, that is the system is macroscopic. This is a fundamental law in nature which is never violated and has led us to a very large number of discoveries in subatomic physics. Thank you.